Welcome to this Quantum Security and Defense presentation, title, High-Level Quantum Programming with CRISP, and thank you for being a valued member of our community.
René Zander completed his PhD in mathematics, specializing in discrete, integrable systems at Technische Universität Berlin in 2020. He joined Fraunhofer FOKUS in 2023, where he has been focusing on quantum benchmarking, post-quantum cryptography, and quantum algorithms research. As part of his work at Fraunhofer FOKUS, René Zander continuously contributes to the further development of the high-level quantum programming language CRISP, under the scope of the Eclipse Foundation.
Yes, thank you very much for the introduction. Do you see my slides? Okay, thanks. Okay, yeah, so I want to give a talk about high-level quantum programming with CRISP and Shor's algorithm. And in the first part of this presentation, I start with quantum programming in CRISP in general. And yeah, basically today, or well, until recently, quantum programming, quantum algorithm development was mainly done via constructing quantum circuits. And this is, I guess, similar to how classical computers were programmed 50 years ago. And it's, of course, very slow, unstructured, and it can't be modularized. And this was basically the motivation for developing yeah, a high-level quantum programming language to simplify aspects of software development and really make it possible to achieve quantum advantage for different fields of applications and make it possible for domain experts to use quantum computing. And yeah, so this was the idea behind developing Eclipse CRISP, which is a fully compilable high-level quantum programming framework. And the central building block is the quantum variable and not the quantum circuit. So basically it's equivalent of working with classical variables in classical computing. And this significantly enhances different development aspects like fast prototyping, shorter code size, and of course makes it easier to have modular code and yeah, further aspects. And a small example is for this approach and about working with variables and functions instead of qubits and gates is this short code block that you see on the right side, where we basically, we have quantum variables and types, and here we have variables of the type quantum float, which is the equivalent of the classical float. And we can do a simple multiplication operation. And this code is fully compilable to the circuit level and can be executed on real quantum hardware like IBM or IQM or other quantum devices. And with this print command, it gets executed on the integrated classical simulator. And the result would be 12, of course, with probability 100%. But if you execute this on today's noisy quantum hardware, you will get some probability distribution, and it won't be 12 with 100%, but 12 maybe with 50%, and then some noise, basically. And now here's some comparison between CRISP code and code from other quantum programming frameworks, and you can clearly see that the CRISP code on the left side looks much simpler and is much more human readable than it would be in other programming languages where you would have to really build the quantum circuits and execute individual quantum gates and so on. And we really think that this, of course, this is just a very small example of code, but if you really want to write large programs, then of course the situation would become much worse. And so we think that that's really necessary to be able to write high-level code to solve more complex problems. And it also, the systematic approach also shows its advantages in terms of different metrics like circuit depth, counts of gates or counts of qubits. And So that was a short introduction, and basically, yeah, Crisp is open source. We have our website, crisp.eu, and the development is open source on GitHub, and you can install it, of course, also via pip install Crisp. And so some further details on Crisp. So yeah, it's an extensive quantum programming framework, and the main features are first typed quantum variables, which I already showed, a library of quantum algorithms and quantum algorithmic primitives like quantum Fourier transform or quantum phase estimation that are basically the building blocks of more complicated quantum algorithms. Then Crisp aims to be compatible with most quantum hardware backends and also different quantum simulators. It features automatic uncomputation, which in some sense can be seen as similar to garbage collection in classical computing, but actually there's actually even more to it in quantum computing. And we have the built-in arithmetic that I showed to you, so that the user can just use arithmetic operations like one would do in normal Python code and does not have to worry about the circuits behind it. And we also have a very fast integrated simulator that makes it possible to execute code and test it on your laptop, which is really helpful since quantum hardware is not widely available yet and still also not reliable yet.
You can join the QU SecDef community to watch the full version of this and over 80 other lectures on quantum technologies, attend events, receive free training, and more. QSecDef is a users community with over 700 members working to forward quantum secure communications. The community is represented by Quantum Security and Defense that provides supply chain orchestration and consulting services on behalf of our members. Find out more. Google quantumsecuritydefense.com.